Good morning, ladies and gentlemen. We're going to start Chapter 4 today. This is Section 4.1, Extrema on an interval. In Chapter 3, we found the different ways to find derivatives with all those rules, the product rule, quotient rule, and chain rule. Now that we're done with Chapter 3 and how to find derivatives, we're going to start applying and finding uses for those derivatives. And one of the first uses is finding these what are called extrema on a given interval. And extrema are just some of the more interesting points on a graph. If we think about, a real simple function here, I'll just draw a curve. Some of the more interesting pieces of this graph are the extreme values, or the extrema, maybe the top of this hill. On this interval, that is the highest value on the y-axis that graph takes on. Or down here in the bottom of this valley, this will be another extrema, another minimum value. And in this section, we're going to understand the definition of extrema of a function on an interval. We're going to understand the definition of relative extrema of a function on an open interval, and be able to find extrema on a closed interval. So, extrema of a function. In calculus, much effort is devoted to determining the behavior of a function on some interval I. Does f have a maximum value? Does it have a minimum value? Where is the function increasing? Where is it decreasing? In this chapter, we're going to learn how derivatives can be used to answer these questions. You'll also see why these questions are important in real-life applications. So here in the definition box, we have the official definition of an extrema. Let f, some function, be defined on an interval I containing point C. Number 1, f of c is a maximum of the function f on that interval if f of c is less than or equal to all other f of x's on that interval. And 2, f of c is a max of f on that interval I if f of c is greater than or equal to all other f of x's across that interval. That might be kind of confusing. I think it's easier to see maybe graphically. Here's our xy axis. And let's say we have a parabola opening up. And what this first part says is f of c is a minimum if f of c is less than all other f of x's. Well, if this is our c value, and that is mapped to the function and then over to the y-axis, this here would be f of c. And if we look at points to the left or the right of c, and we map those up to the function and over to the y-axis, we're going to see that those values are higher than f of c. So back up here it says f of c is less than all other f of x's. Well, here this f of c is the lowest on the y-axis. Any other x value we put into the function will turn up to be a higher value on the y-axis. And the inverse of that would be true for the idea of a maximum. Again, here's our xy axis. Maybe we have a downward opening parabola. And if we plug in this c value, when it goes up to the function and is mapped to the y-axis, here's f of c. If we pick other values around c, and let's say this one goes up to the function and over, that value is less than f of c. Same here. This value is mapped over to the y-axis. If we come back up here to number 2, f of c is a max if f of c is greater than all other f of x's. Well, here we can see that f of c is going to be greater than these other values of f of x. So the min and max of a function on some interval are also called the absolute min, or the absolute max. Or other books might call it the global min, or the global max. Those are just the most extreme high and extreme low functions that are values that this function will take on a given interval. And here's 3.1, the extreme value theorem, or the EVT. And what the EVT says is if f is a continuous function on a closed interval from a to b, then f, the function, has both a min and a max somewhere on that interval. And let me highlight a couple of the key pieces here. It has to be a continuous function on a closed interval. Those are key. The function must be continuous and it has to be a closed interval. Now here on this first graph, if we look at the function, we do have an interval from -1 to 2. It is a closed interval, so the endpoints are included. And looking at the graph, we can see that it is continuous. So this meets both the requisite pieces here of the extreme value theorem. It's continuous, it's a closed interval, so the EVT says there will be a max and a min somewhere on that interval. And if we just look at the graph, the lowest point we see on the graph is right here, 0, 1. That's our minimum value. The highest value on the y-axis that this function contains on the interval happens to be this right endpoint. At the right endpoint, we have a value of the function of 5. So the EVT, we had the continuous and closed interval. We were guaranteed a min and a max, and there they are. The min and the max we easily found. Let's take a look at this second graph. Now here the function is continuous. We do have a continuous function, but the interval is no longer closed. Now it's an open interval. We have parentheses around our endpoints, and in the graph we do not have closed circles at the endpoints. We have these open circles. So by the EVT, our function is continuous, but it's not closed. So we are not guaranteed a min and a max on that interval, but we still might be able to find them. Here we can see at the bottom of this curve, we do have our lowest value is again at 0, 1. That is our minimum value. But when it comes to a max, in the previous graph, this was a closed interval, or a closed dot, so the endpoint was included, and that happened to be our max. But is there a maximum here? You know, if we think about the idea of a limit as we approach that hole in the graph, you know, as we approach it, there's always one point that's just a little bit closer. We can get closer and closer to this open endpoint without ever actually getting there. So there is not going to be a maximum value of this function on that interval. And let's look at our last example. Now here we see our endpoints are back. So the function is closed. We are back to a closed interval. But here the function is not continuous. As we're looking across this curve, we see we have a hole in the graph. And we also go up that we do have a value defined there, but it is removed from the function itself. So if we want to look for a maximum, now that we're on a closed interval again, we have this dot is filled in, we do have our maximum value again here at 2, 5. But is there a minimum value? We see down here is a valley. In the valley though, somewhere near the bottom, there's a hole in the valley. Again, if we take the idea of a limit, we're approaching the hole in the graph from either side. But we're not actually going to get there. You know, for every point we choose close to the hole in our graph, there's always another point closer. We can get infinitely close to that hole in the graph without ever actually getting there. Since we can never attain that actual value, there's no minimum on this interval for that graph. Again, the key parts here are we have to have a continuous function on a closed interval. Then we are guaranteed both a min and a max. Now, relative, extrema, and critical numbers. In figure 3.2, over here on the right, the graph of f of x is x to the third minus 3x squared has a relative max at the point 0, 0, and a relative min at 2, -4. Again, here's our relative max, here's our relative min. Informally, for a continuous function, you can think of a relative max occurring on a hill of the graph. A relative min occurs in the valley of a graph. Such a hill and valley can occur in two ways. If the hill or valley is smooth and rounded, the graph will have a horizontal tangent line at that high or low point. If the hill or valley is sharp and peaked, the graph represents a function that's not differentiable at that high or low point. And here in our box we have the official definition of a relative extrema. If there's an open interval containing point C on which f of C is a maximum, then f of C is called the relative max of the function f, or you could say that f has a relative max at the point C, f of C. That's just its x and y coordinate. If there's an open interval containing point C on which f of c is a minimum, then f of c is called a relative min of the function f, or you can say it has a relative min at the point c comma f of c. The plural of relative max is relative maxima, and the plural of relative min is relative minima. Remember, maximum and relative minimum are sometimes called local maxes and mins. And let's dive into example 1 here. This is very similar to the first few homework questions assigned for this section. So example 1 examines the derivatives of functions at given relative extrema. Much more is said about finding these extrema later on. So here in this example, they're handing us the relative extrema on a silver platter. Here's our point. They're telling us that is the relative max, and it has a value of 3, 2. Our function is given here in the blue box, 9 times the quantity x squared minus 3 all over x to the third. And what they're asking us to do here is find the value of the derivative at this point. So, we have our given function, f of x is equal to 9 times x squared minus 3 quantity, all divided by x to the third. And what they're asking us to do is take the derivative and make sure that that derivative is equal to 0 at the value x is 3. So we're going to have to take this derivative with the quotient rule. So if I look at just my numerator, and if I distributed the 9, I would have a term of 9x squared. The derivative of 9x squared is going to be 18x. And if I look at my denominator, x to the third, the derivative of the denominator is 3x squared. So I'm going to do the quotient rule. Low d high minus high d low over low low. Low d high. So I'm going to multiply on this sort of diagonal. X to the third times 18x. Minus high d low. So I'm going to multiply sort of on this diagonal. And right off the bat, I'm going to multiply the 9 by the 3x squared and get 27x squared times the quantity x squared minus 3. And that is all over low d high minus high d low over low low, or x to the third times x to the third. And let's start to clean this up a little bit. If we distribute here, we're going to get 18x to the fourth, minus here we're going to have 27x to the fourth, plus 3 times 27 is 81x squared. And then our denominator is x to the third times x to the third is x to the sixth. And let me get rid of some of this clutter. All right, and if we simplify that numerator a little bit, 18x to the fourth minus 27x to the fourth gives us negative 9x to the fourth, plus 81x squared, 81x squared, all over x to the sixth. And now I see that every term has an x term in it. So what we can do is simplify here a little bit and sort of factor out an x squared. So I can eliminate this x squared. This will get knocked down to a second power, and this will get knocked down to the fourth power. And I'm going to rewrite it so my negative term isn't my first term. So I'm going to do 81 minus 9x squared all over x to the fourth. And I can see here I can factor a 9 out of that numerator also. I pull a 9 out of there, and I'm going to have 9 times the quantity, 9 minus x squared, all over x to the fourth. So we have the derivative. This is f prime of x. F prime of x is equal to this quantity. Now what they're asking us to do in this problem is just to verify that this is the relative max. So if I plug this x value in, an x value of 3, into this derivative, I should get a value of 0. So let's give it a try. F prime of 3 is going to be equal to 9 times the quantity 9 minus, instead of x squared, we're plugging in a 3. 3 squared, all over x to the 4th. And when I look at this here in the parentheses, I'm going to have a 3 squared is 9. 9 minus 9 is 0. Times this 9 is still 0. And I'm going to wind up with 0 divided by 3 to the 4th. 0 divided by anything is 0. So the value of the derivative at this x value is in fact 0, just like we were expecting to find. Again, this example is a lot like the first few homework problems assigned for this section. Let's look at part B here. In part B, we want to find, here is our relative min. It is given down here as 0. Our given function is f of x is equal to the absolute value of x. And again, the directions were to find the value of the derivative at this min. They handed us the min. It's at 0, 0. We need to take the derivative of this and, in fact, find out that the derivative has a value of 0 at that point. But we run into a little problem. We want to take the derivative of this function. Can we take the derivative of this function at any given point? And this graph should look familiar. We've been talking about these absolute value functions several times throughout the course. Does the derivative exist at this sharp corner? No, it does not. If we remember back to our limits, let's look as we approach from the left side. The limit, as x approaches 0 from the negative side, is equal to, remember the derivative is just what's the value of the slope of this. The slope here is negative, and it's in fact -1. If we look from the other side, the limit, as x is approaching 0 from the positive side, over on this side, we have a positive slope. Here the slope is +1. So the derivative from the left is different from the derivative from the right, and therefore the derivative does not exist. Derivative dne does not exist for this function at that point. Part C, we want to find the value of the derivative at the extrema shown. And here this is the sine function. F of x is equal to sine x. And they're telling us here that we have a relative max at ½ pi radians, and here we have a relative min at 3½ pi radians. They just want us to verify that those in fact are relative mins and max. So the derivative should have a value of 0 at those points. So let's take the derivative. The derivative of f of x, f prime x. The derivative of sine is cosine x. So let's evaluate this derivative at the given possible extrema. F prime of ½ pi is equal to the cosine of ½ pi. What is the value of cosine at ½ pi? Well, if we think back to the unit circle, at least here are our axes, and our most important points on there are 1, 0. This would be 0, 1. Here we would have -1, 0. And down here would be 0, -1. We're looking for the cosine of a ½ pi. ½ pi is our positive y-axis. The cosine value is our x value. So here, cosine of a ½ pi is in fact equal to 0. And let's evaluate at the other given extrema, 3/2 pi. F prime of 3/2 pi is the cosine value at 3/2 pi. 3/2 pi is our negative y-axis, and here again is our cosine value, is our x-coordinate. So again, we do find out that the cosine of 3/2 pi is equal to 0. So at these points, these are our extrema, they would have horizontal tangent lines. Okay, note in example 1 that each relative extremum, the derivative is either 0 or it does not exist. The x values at these special points are called critical numbers. Critical numbers are just the x values of these extrema. Figure 3.4 illustrates two types of critical numbers. Notice the definition that the critical number c has to be in the domain of the function. but c does not have to be in the domain of the derivative. So here's our definition of a critical number. Let f be defined at some point c if f prime of c is equal to 0, or if f is not differentiable at that point, then c is a critical number. So here in the first graph, we have a very sharp point above our x value of c. This is going to be a critical number, but the derivative doesn't exist. Here in the graph on the right, we have a nice smooth parabolic curve opening downward. Here's our point c. And above point C on the graph, we have our point, and there is in fact a horizontal tangent line there. That horizontal tangent line means the derivative has a value of 0. And we're going to end this first video here. I don't want to make them too long, so we're going to pick up in the second video with finding extrema on a closed interval.